Imagine drifting through space when, ahead of you, the stars begin to bend. Their light stretches into glowing arcs, and the darkness at the center seems deeper than anything you have ever seen. You are approaching a black hole, an object whose gravity is so powerful that beyond a certain boundary, nothing can return. Not matter, not radio signals, and not even light. So, what would actually happen if a human fell into one? The answer depends on the black hole. You might be torn apart long before reaching it, or you might cross its event horizon without immediately noticing anything unusual. But once you pass that boundary, your fate is sealed. A black hole is not simply a giant hole floating in space. It is a region where an enormous amount of mass has been compressed into an incredibly small volume. The most familiar black holes form when massive stars exhaust their nuclear fuel. Without the outward pressure created by fusion, the star's core collapses under its own gravity. If the remaining core is massive enough, no known force can stop that collapse. Around every black hole is a boundary called the event horizon. This is the point of no return. Outside it, escape is theoretically possible. Inside it, every possible path through space and time leads deeper into the black hole. Suppose you begin falling toward a black hole with the mass of several suns. At first, you would feel almost weightless. This may sound strange because the black hole's gravity is extremely strong, but you are in free fall, just like an astronaut orbiting Earth. Everything around you, including your spacecraft, is accelerating at almost the same rate. The real danger is not gravity itself. It is the difference in gravity between one part of your body and another. As you fall feet first, your feet are slightly closer to the black hole than your head. They therefore experience a stronger gravitational pull. At the same time, the sides of your body are squeezed toward the center of your fall. You are stretched vertically and compressed horizontally. Scientists call these differences tidal forces. The more closely you approach the black hole, the more extreme they become. Eventually, the force pulling on your feet would become vastly stronger than the force pulling on your head. Your body would stretch like a strand of spaghetti. This process has an appropriately dramatic name: spaghettification. At first, your muscles and bones would resist, then your joints would separate, your tissues would tear, and even individual cells would be pulled apart. Closer still, molecules would be broken down. Under sufficiently extreme tidal forces, atoms themselves could be disrupted, leaving a stream of subatomic particles descending into the darkness. For a small stellar mass black hole, this would probably happen before you cross the event horizon. You would never reach the point of no return as an intact human. But now imagine falling toward a supermassive black hole like the one at the center of the Milky Way. Sagittarius A star contains about 4 million times the mass of the Sun. Other galaxies contain black holes that are billions of times more massive than the Sun. Surprisingly, a larger black hole may give you a gentler journey through its event horizon. The event horizon of a stellar mass black hole may be only a few dozen kilometers across. All of its mass is concentrated within a very small region, so the gravitational field changes dramatically over the length of your body. A supermassive black hole has a much larger event horizon. At that boundary, the difference between the gravitational pull on your head and your feet could be relatively small. You might cross the event horizon alive and without feeling a sudden impact. There would be no solid surface to strike. There would be no glowing wall and no alarm announcing that you had entered the black hole. Locally, the laws of physics could appear completely normal. If you were sealed inside a small spacecraft with no windows and only performed experiments on nearby objects, you might not be able to identify the exact moment of crossing. But an observer watching from far away would see something very different. As you approach the event horizon, your clock would appear to run more slowly. Every movement would seem increasingly delayed. The light coming from you would also lose energy as it climbed out of the black hole's gravitational field. Its wavelength would stretch toward the red end of the spectrum in a process called gravitational redshift. To the distant observer, you would seem to slow down, fade, and become redder. They would never see you clearly cross the event horizon. Your final image would become dimmer until it disappeared. From your perspective, however, your own clock would continue normally. You would cross the horizon after a finite amount of time. You would not see the entire future of the universe flash before your eyes. Light from the external universe could appear distorted and accelerated in complicated ways, but the popular idea that you would witness infinite cosmic history during the fall is misleading. Communication would become increasingly difficult. Before crossing the horizon, you could still transmit signals outward, although they would reach distant observers with longer delays and less energy. Once inside, no signal you sent could escape. This does not happen because your radio transmitter is too weak. Even a perfectly powerful beam of light pointed outward cannot leave. Inside the event horizon, moving toward the center is as unavoidable as moving toward tomorrow. In ordinary space, you can choose to travel north, south, east, or west. You cannot choose to stop moving forward through time. Inside a black hole, the central region plays a similarly unavoidable role. Every future-directed path leads inward. Trying to escape would be like trying to travel back into yesterday. If the black hole were rotating, and most real black holes probably are, the experience would be even stranger. A rotating black hole drags space-time around with it. This effect is called frame dragging. Outside the event horizon is a region known as the ergosphere. Within it, space-time is being dragged so strongly that nothing can remain completely stationary relative to the distant universe. You would be forced to rotate with the black hole. In principle, objects interacting inside the ergosphere could extract a small amount of the black hole's rotational energy, but this would not offer you a realistic rescue once you had crossed the event horizon. The view around you would also become deeply distorted. The black hole's gravity bends light, allowing you to see multiple images of the same stars. Light could travel around the black hole before reaching your eyes, producing rings, arcs, and a warped panorama of the universe. If the black hole were actively feeding, however, the view might be the least of your problems. Many black holes are surrounded by accretion disks, vast rings of gas, dust, and shredded material orbiting at extraordinary speeds. Friction and magnetic forces heat this matter to millions of degrees. The disk can release intense X-rays and other high-energy radiation. Some active black holes also launch enormous jets of particles at nearly the speed of light. These jets can extend far beyond their host galaxies. Approaching such a black hole would probably kill you through radiation long before gravity tore you apart. For the cleanest possible fall, you would need a quiet, isolated black hole with little surrounding material. Suppose you manage to cross the event horizon of a quiet, supermassive black hole. You are alive, at least temporarily, but you cannot turn around. As you descend, the tidal forces grow stronger. Spaghettification has merely been delayed. Your remaining time would depend on the black hole's mass and rotation. For a stellar mass black hole, the interval between crossing the horizon and reaching the central region could be only a tiny fraction of a second. Inside a supermassive black hole, you might have seconds or possibly much longer, depending on its size and the exact path of your fall. But what would you ultimately reach? According to classical general relativity, matter collapsing inside a black hole forms a singularity. In the simplest non-rotating model, this is described as a point where density and the curvature of space-time become infinite. In a rotating black hole, the mathematical structure is more complicated and may involve a ring-shaped singularity. However, physicists do not generally interpret this as proof that a literal infinitely dense point exists in nature. Instead, the singularity probably tells us that general relativity has reached the limit of its usefulness. To understand what truly happens there, we would need a theory that successfully combines gravity with quantum mechanics, a theory of quantum gravity. Scientists are exploring possibilities such as string theory and loop quantum gravity, but no complete theory has yet been experimentally confirmed. This means that the final stage of your fall is unknown. Classical physics predicts that you are inevitably crushed at the singularity. A future theory might replace the singularity with some extremely dense quantum structure. It might reveal entirely new behavior of space-time. But there is currently no evidence that falling through a black hole would carry you safely to another universe, through a wormhole or into a different point in our own galaxy. These are fascinating possibilities in equations and science fiction, not established escape routes. There is another mystery. Quantum mechanics suggests that information cannot simply be destroyed, but if an object falls into a black hole and the black hole eventually evaporates, what happens to all the information describing that object? Black holes are not completely black. Stephen Hawking showed that quantum effects allow them to emit extremely faint thermal radiation. Over unimaginable periods, a black hole can lose mass and eventually evaporate. For an astrophysical black hole, this process is extraordinarily slow. A black hole with roughly the sun's mass would survive for around 10 to the power of 67 years, vastly longer than the current age of the universe. Supermassive black holes would last even longer. Hawking radiation would therefore not save you, nor would it meaningfully affect your fall. But it creates the famous black hole information paradox. If the radiation contains no information about what entered the black hole, quantum mechanics appears to be violated. If the information does escape, physicists must explain how. Some ideas suggest that information is somehow encoded on the event horizon. This helped inspire the holographic principle, the possibility that information contained within a region of space can be described on its boundary. Other proposals involve subtle correlations in Hawking radiation, quantum connections, or dramatic structures near the horizon. One controversial idea, known as the firewall hypothesis, suggests that an energetic barrier may form at the event horizon and destroy anything attempting to cross it. This would contradict the prediction of general relativity that a person entering a sufficiently large black hole might notice nothing special at the horizon. No one currently knows which description is correct. So what happens when a human falls into a black hole? Near a small black hole, tidal forces would tear the person apart before they reach the event horizon. Near a quiet supermassive black hole, they might cross the horizon alive, perhaps without recognizing the exact moment it happened. To distant observers, they would appear to slow, redden, and fade. From their own perspective, they would continue falling normally, unable to communicate with the outside universe. Deeper inside, tidal forces would inevitably become lethal. The person would be stretched, compressed, and broken down into particles. Classical relativity says those particles would reach a singularity. What happens at the final quantum level remains one of the greatest unanswered questions in physics. Falling into a black hole would not reveal a peaceful tunnel through space, and it would not allow you to watch eternity pass outside. It would be a one-way journey into a region where space and time behave in ways that challenge our deepest understanding of reality. And although no human is likely to take that journey, black holes allow us to test the limits of our best theories. They force us to ask what space is, what time is, whether information can truly disappear, and where the known laws of physics finally break down. At the edge of a black hole, we are not only looking into darkness, we are looking at the boundary of human knowledge.